Hi, this is Professor Fernandez, and we're going to talk about equations of planes in this module 2 in lesson 3. So let's think a little bit about this word planes. And before I get there to the math, I just want to talk about what a plane is. So you probably already know this, but a plane is a two-dimensional flat surface. And really, the math version of a plane is a two-dimensional flat surface that goes on forever. So, a sheet of paper is a good example of something that's almost a plane, but, it's finite, so it doesn't go on forever. But if you lay it flat on a table, it's two-dimensional, it's flat. So, you can kind of think of it as a toy model of a plane. So how might we mathematize this? How might we come up with an equation of a plane? Well, the first thing I want to go to is something a bit more familiar. So let's talk about ax plus by equals d. So this is the pretty general equation of a line in R2, right? We can solve for y and put this in y equals mx plus b form. It might be more recognizable. But this form is a bit more general because if, for example, b is 0, then this allows us to be able to talk about lines like x equals 4, which is a legitimate line that cannot be put in y equals mx plus b form. So this form of the equation of a line in R2 is something that we can easily, use to guess the equation of a plane in R3. We did a little bit of this in the first lesson where we thought about the fact that, hey, this is the equation of a circle in R2. Maybe if we just add a z squared, might this be the equation of a sphere in R3? And that exactly turned out to be the case. So we're going to do something very similar here just to get a guess for where we might want to head in figuring out the equation of a plane. So what if we just tack on a cz, a term right here. So I'll put it in red so we see what the new part is. Plus cz equals d. Might this be the equation of a plane in R3? Well, so we have, somewhat good reason to suspect that. This seems to be a pretty natural generalization of, the straight, quote, surface in R2 that we know as a line, flat. So we might think, okay, this might be the equation of a plane in R3. It turns out to be true. So this is what we're going to show below using vectors, actually. So let's start doing that now that we have a rough idea of where we're heading. First thing I want to do is I want to draw you a picture. So here is, a plane. Let's just think of it as this little sheet of paper so that it is easier to draw. I don't have to draw it all to infinity. One thing that's very useful in figuring out the equation of a plane is to realize that every plane carries with it what's called a normal vector. This is a vector that is perpendicular to the plane. And this is, there whether you see it or not. If you have a sheet of paper in front of you or can grab one and you get it and put it on top of a table, you can certainly put your pencil in the direction that is perpendicular to the sheet of paper. That's the normal vector. And this doesn't matter if you have a plane that's rotated in some other way, you can still define a perpendicular vector, a vector that's perpendicular to the plane, a normal vector. So what we're going to use is this basic fact to help us write out the equation or derive the equation of a plane. So how are we going to do that? Well, the first thing I want to do is I want to say, okay, it's also a plane and also has a bunch of points on it, infinite number of points. Let's pick one, call it p sub 0. And let's pick this p sub 0 point out of convenience just to be the initial point of the normal vector, the vector that's normal to the plane. And then next thing, what am I going to do? I'm going to say, okay, well, you know what? The plane has an infinite number of points on it. All these red points are on the plane. Let me just pick one of them. Let's pick this green one here. And let me call that point P. And let's say its coordinates are x, y, and z. Great, so far I've picked out three aspects of this plane. Its normal vector, the initial point that is on the plane, I'm assuming, p sub 0, and this other point p on the plane also. And out of these three elements, I am going to generate the equation of the plane, which is going to end up looking just like that. How are we going to do that? Okay, so we're going to use a little bit of vector geometry here. So let me put this plane into a set of XYZ axes. And let's get some vectors going here. So I'm going to call the vector from the origin to the point P sub 0, R sub 0. And then let's call the vector from the origin to the point P, R. Okay. Using that, I can then come up with the equation of the vector from P sub 0 to P. That's that one right there. So that is P sub 0 P vector. Or we can also call it R minus R sub 0, right? Using some of the vector addition, subtraction that we talked about in the last lesson. Great. So what do we see? If I look now, I've tried to put in the same color, and I pop this out. We have a normal vector. We have a vector P0, P, and then we have a 90-degree angle here. We can now use what we learned about dot products. So these two vectors are perpendicular, right? That's kind of what we saw from all these properties of points on a plane and the vector n being a normal vector. So we can say that, and I inadvertently put a unit vector here. Normal vectors don't have to be unit vectors. It makes life a little bit simpler, but it doesn't matter. So back to perpendicularity, the normal vector n dotted with the vector P0P, because they're orthogonal, must be 0. Remember we talked in lesson 2 about two non-zero vectors are orthogonal if and only if their dot product is 0. Okay, so far so good. Now I just have to coordinatize everything. We said that right here, that P sub 0, P, that vector, is equal to R minus R sub 0. So, and I have already given some coordinates for R. That is the vector over here that goes from the origin, R sub 0 goes from the origin to P sub 0. These are the coordinates of P sub 0. So that's x0, y0, z0. And then I have this other vector r, which goes from the origin to the vector p. Its coordinates are x, y, z. So the vector p sub 0 p has components x minus x naught, y minus y naught, and z minus z naught. Great, so I'm going to plop this in here. So now I know what I'm dotting in my second vector. And now what about n? Well, I'm just going to assume, let's assume that n has components a, b, c. And from this, I can then expand out the dot product. And using what we know about how to calculate dot products, multiply the x components together, add the product of the y components, add the product of the z components. Great. And that gets me to pretty much the equation that we thought we were going to get to up here. The d comes from the fact that if I multiply a times x naught, b times y naught, c times z naught, I get a bunch of negative terms. When I add it to the right-hand side, that's my magic d. So we have derived the equation of a plane, and that's this definition down here. So let's see what it says. It says, suppose p equals x naught, y naught, z naught, and n is a normal vector. Then the equation of the plane passing through p, having normal vector n, is the thing we've just derived. So that's great. This is the standard form of the equation of the plane. In this form, it is easy to read off both the normal vector, a, b, c, and the point that is on the plane. If, however, you do what I said and you multiply all these three things together and then add the result to the right-hand side, that's where you get this d. So you may also sometimes see the plane in what's called a general form. It's a little harder from this form to pick out a point on the plane, but you can do it. You can pick an x value, pick a y value, for example, and then solve for z. You can try that. So, but anyway, this is the other form of the equation of a plane. Great, so that is pretty much it in terms of deriving the equation of the plane. So what I want to do now is do a couple of examples and then illustrate for you how this also relates to the cross product. We'll see that in this example down here. Okay, so let's do example 3.2 first. Find the equation of the plane passing through this point and with normal vector this. Great. So if you have now internalized, it might take a while to do so, but how we got to the equation of the plane, we got there by doing the dot product of r minus r sub 0 with the normal vector equals 0. In this case, the normal vector is 2, 3, 4. And the r sub 0 vector, sorry, r minus r sub 0 is x minus the x component of the point that you know is on the plane, y minus the y component of the point you know is on the plane, and then z minus the z component equals 0. And then we just calculate the dot product. 2x minus 2 plus 3y minus 4 plus 4z plus 1 equals 0. If I multiply these things out, I can simplify things a little bit, and you can check this, that if you add it to the right, here you're getting negative 4 minus 12, that's negative 16, plus 4, that's negative 12, and then you add it to the right-hand side, you get positive 12. So that gets you there. So this is our equation of the plane in this general form, or we could have left it in this way, and this would have been the equation of the plane in this standard form. So I want to show you visually what this looks like. I could attempt to draw a picture, and I will in a minute, but I'll also show you, using some technology, what this looks like. First, the picture. So how would we draw a picture? I'm going to draw you a very simplified picture, and then we will use technology to get us much more information. So what's the simplified picture I'm going to draw you? Well, it's pretty easy once you have the equation of the plane to look at the first octant of the plane, the portion of the plane in the first octant, to see what it looks like. How do you do this? So you look at the intercepts, just like you would a line, and that'll give you an idea of what the line looks like. When x equals 0, and, well, let's start off with finding the x-intercept. So that's when y and z are both 0. So that implies that if y and z are both 0, this is gone, 2x is 12, so x equals 6. So I get x equals 6. So I'm going to go here and just be lazy and pretend that's 6 and put a point. And then I'm going to do the same thing. So I'm going to look at the other intercepts. So how about we do x equals y equals 0. So if I get rid of x and y, then I'm just left with 4z equals 12. So z equals 3. Great. And then if I do, how about x and z are 0, then I get rid of x and z, and I get 3y equals 12. So y is 4. Okay, so this was, I'm going to try to make it slightly to scale here. Y is 4, and then z is 3. So remember that 3 points from geometry class, 3 points determine a plane. 2 points determine a line. So I have 3 points now, so if I just connect them all, I get some sense of what my plane looks like. Okay. Again, as I said, this is not the best visualization ever. I am human, and I will shortly show you something better. But still, this gives you a rough idea of what this plane looks like, and how much it slants in the x, y plane, in the y, z plane, in the x, z planes. Okay, so it also gives you a sense of how, if you were only able to draw this by hand on some assessment, a quiz, or an exam, you might, try this without needing a calculator or technology or something. All right, so I'm going to switch over. I have put this into this really useful site called Calc Plot 3D, and you see the web address up there. So let me just really quickly turn on my wannabe mouse here so I can move around. So, okay, so this is the website up here. If you Google Calc Plot 3D, you'll see that. If you hit this menu button and you put implicit surface, I believe it is, you can write in the equation. So I've put in the equation that we just got, and then you can specify the x and y bounds. And then if you go up here to this button here, you can also change the actual graph window. So what I've done here, and then you can specify how many, basically how well you want the program to try to numerically draw the surface. So this is the surface here, so I'm going to just pan around and show you what's going on. One thing to know, once I start moving things around, it's actually very hard to get the axes back to look like this, where this is x, this is y, this is z. So you'll see things move around a lot, but it'll give you some sense of what's going on. You can already see, here's the 6. So you can see that the plane is actually crossing the x-axis at x equals 6, as we saw it would. And then it's doing it similarly at the y-axis. Here's y equals 4, and here's z equals 3. So even with my very limited drawing skills, I've captured some of the basic behavior of the plane. Okay, so here we go. So there I am rotating things around, and my axes are, as I mentioned, kind of floating around on me. But you can see from different directions. First of all, clearly you see a flat two-dimensional surface in 3 dimensions. So that's a plane. And also you only see a part of it. Because again, I've set all the axes to go from -6 to 6. You can kind of see that down there. But anyway, this is the plane. So beyond this, there's not much that insight that I can give you. You can see that if I look at it, on the plane, if I'm kind of looking at it on its side, there is certainly a normal vector here that we could define. And it points kind of like, certainly away from the plane, as all normal vectors do. But if it's possible for you to visualize what the vector 2, 3, 4 is, it has a positive x component, positive y component, positive z component. So it points like almost like radially away from the origin, which, looking here would be something like going that way, right? So that's if you're going this way in x and this way in y and this way in z at the same time, you're pretty much going that way. So even though the normal vector is not pictured here, we can kind of superimpose it by just thinking about the fact that its components are 2, 3, 4. Okay, so I'm going to switch back, and that's about all I want to say about that example. This was the first example because the normal vector is given, and so is the point. Let's talk about this other example where we are given different information to start with. We're given 3 points. So here things are slightly trickier. We're not given a normal vector. We're not going to use necessarily just borrow the equation right away that we derived. But that's okay. Because again, going back to how we derived everything, right? We had a point here, and then I drew a bunch of points everywhere else. And we had a normal vector, so we used that normal vector, and then we created one of these vectors and the dot product that gave us the equation of our plane. We don't have a normal vector now, but we know for sure that we have at least 3 points. So what can we do? Here's what we're going to do. We're going to create 2 vectors from these 3 points. Let's call these points, I don't know, let's use P as our anchor. So how about this is P, this is Q, this is R. So, this vector is going to be PQ vector, and then this vector is going to be PR vector. So now we have 2 vectors that are in the plane. We still want a normal vector so that we can use our equation that we just derived. So how could we possibly get a vector that's orthogonal to both of these vectors? So now we're back to the first module in this lesson. So we're back to the cross product. So that's right. So our normal vector that we are going to build, n, we are going to build it by crossing PQ with PR. PQ and PR. And that's going to give us this normal vector. And then we're back in business. So we have a normal vector, we have a point, and then at that point we just follow the procedure we did in the previous example. Okay, so this is, intended to illustrate how things change if you are given 3 points instead of a point and a normal vector, but effectively how things stay the same you want to get to the same point eventually. Get the normal vector, use the point on the plane, and then use the equation we derived. Okay, so this throws us back into calculating cross products. First, though, we got to calculate PQ and PR. So let's do that. So PQ is the vector that goes from P to Q. So we are going to look at the points P and Q, and we are going to basically subtract. So PQ is 3 minus 2. That is, let's see here. Yes, yeah, 3 minus 2, that's 1. And then we have negative 1 minus 4, so that's negative 5. And then we have 6 minus negative 1, 6 plus 1, 7. So that's our PQ vector. And then we have PR, and let's see what that looks like. So we are going to now use P and our R vector over here, our R point. Okay, so the X component 5 minus 2, so that's 3. Y component's 2 minus 4, negative 2. And then 0 minus negative 1, so 1. Okay, so we have our P and our Q vectors. And at this point, we are going to go off and find their cross product. So remember how this goes from the previous video from module 1 in this lesson. We're going to take the cross product here. N is a normal vector of these PQ and PR vectors. So we put them in this 3 by 3 matrix. We have 1, negative 5, 7, 3, negative 2, 1. And then we write this out in terms of the sums of multiples of determinants of these 2 by 2 submatrices. So the I hat 1 is the submatrix minus 5, 7, minus 2, 1. The J hat 1 is this submatrix. So 1, 7, 3, 1, and the K hat 1 is over here. So that's 1, negative 5, 3, negative 2. Then we calculate these determinants. So we have negative 5 minus negative 14, so that's plus 14, I hat. And over here we have 1 minus 21, and then we have a J hat there. And then over here we have negative 2 minus negative 15, so plus 15, and we have a K hat. And then we do some arithmetic here. Negative 5 plus 14, that's 9. And then we over here we have 1 minus 21, negative 20, with a negative out front, makes it positive. And then over here we have plus 13 K hat. So at this point, we have finally gotten our normal vector. There it is. And we can go back and choose any one of these points to be the point that's on the plane. All 3 of them are. I'm going to choose the anchor point we've been working with. So we have our points 2, 4, negative 1, just to check again that that's it. Yep. So now we can just use the equation of the plane that we developed. So it's A, where A is the x component of the normal vector, times x minus x component of P, plus y component normal vector, y minus y component of P, plus z component of the normal vector, z minus z component of P, equals 0. And that's our equation of this plane. Great. So I won't plot this one. I encourage you to go to Calc Plot 3D to play around with the interface and see if you can plot this plane. But just as a recap, let me go back to the equation, the definition of the plane. So recap, we have remembered a little bit about planes and used our intuition to get us to the point where we realize that if I have a normal vector and I have a point on the plane, then the dot product enables us to write down this standard form of the equation of a plane. The general form effectively just multiplies and puts all these constants on the right-hand side. That's the D. Advantages, disadvantages. In both of these representations, you can see what the normal vector is, ABC. But in this one, you can also pick out a point that's on the plane. That's x naught, y naught, z naught. That's the point P. In this one, you can't do that so easily. Again, you could choose an x and y value and solve for z. Maybe try that to get a point on the plane, but you just can't see it right away. The first example was intended to just walk through the simplest case where you're given the normal vector, given the point on the plane, and then you just apply the formula. Graphing it, we can use some intercepts to help us get a rough sense of what the plane looks like. As always, technology helps a lot more. In other cases where you have not a given information of a normal vector and a point, but you have 3 points, that's okay. We can form 2 vectors on the plane from them, like we did here, and then we can cross product to find the normal vector, using the properties of the cross product that we learned in the orthogonality properties we learned in the previous module. Then from there, once we get our normal vector, you pick a point and you go back and use our equation of the plane. So that's it for this video, and I'll see you in the next module.